And let's start. So thank you all for coming to the seminar. Today's speaker is Tsukasa Ishibashi at the Mathematical Institute of Tohoku University, Japan. And the title is Moduli Space of Decorated Geolocal Systems and Skein Algebras. Please.
Thank you for your introduction. And thank you for the invitation to this nice seminar. And today, I want to talk on the geometry of the moduli space introduced by Fock and Goncharov of certain decorated geolocal systems on the surface. And so I will talk on its geometry and the cluster structure firstly. And in the latter half of this talk, I want to also mention its quantization via the quantum cluster algebra and its relation to the skein algebras. So this talk is based on these joint works with Hironori Oya and Linhui Shen on the geometry and cluster structure, and with the Wataru Yuasa on its relation to the skein algebras. Okay, so the contents of my talk is summarized in this top page. So firstly, I want to talk on the relation between the function ring of this moduli space in the title, or more precisely, its generic part, and the related so-called cluster algebra. So the coincidence of these two algebras is the first main theorem. And in particular, this equality gives us two distinguished sets of generating functions. So one is the cluster variables, which is the natural generating set for the cluster algebra. And the other is the so-called matrix coefficients of Wilson line functions, which are natural from the geometry aspects. So this equality shows these algebra have these two generating sets. And then we can write down the somehow explicit relations among them. So we have, roughly speaking, we have two coordinate systems and the explicit transition relation between them. And the second topic is its quantization in the framework of the quantum cluster algebra due to Berenstein, Zelevinsky, and Goncharov Shen. It's slight reformulation by Goncharov Shen. Then via the quantization of the cluster algebra, we get the non-commutative deformation of the cluster algebra called the quantum cluster algebra. Then, as a quantization of these relations in a classical level, we propose, as a quantum version, we propose an isomorphism between two kinds of skein algebras, quantizing these geometries. So this is the summary of my talk. So let me explain more details as an introduction. So, so let us begin with the classic setting, which is relatively well known. So let sigma be at first a closed surface of genus grid at least 2. And let G, throughout this talk, G be simply connected as a simple algebraic group over C. So the examples include SLN and spin N of type B or D, and symplectic groups of type C. So given such a pair of a surface and a group, we can consider the the moduli space log G sigma, moduli space of G local systems on sigma. So here, what is the G local systems? So of course, we have several equivalent definitions of G local systems. You may, for example, think of it as a principal G bundle over the surface together with a flat connection. So this is illustrated in this picture. So firstly, the principal G bundle assigns to every point of the surface a fiber isomorphic to G. So we have G parameterized by sigma. And then the data of flat connection determines how to go among the different fibers in the horizontal direction. So we have the power transport among different fibers along the flat connection, right? So for example, if we choose a closed loop on the base surface, we can lift it to the fibers. Then following the flat connection, we get back to the original fiber. But in general, we don't return to the original point in the fiber. And the difference is measured as a monodromy along this loop. Then it is classically well known that this monodromy homomorphism, which is a conjugatory class of the homomorphism from the fundamental group to the gauge group G, completely determines the local system. So, well, if we ignore the way of quotients at first, this gives a bijection between these two sets of objects, right? And in this talk, I want to talk about its function ring in an algebraic geometry sense. So we will take the stacky quotient here. So this is the so-called quotient stack. Well, but you don't need to so much careful about this quotient in this talk, because I want to, well, consider only its function ring of global functions. So yeah, so the function ring is the same as that of the categorical quotient, for example, a GIT quotient. So it doesn't matter much in this talk. But just I fixed the class of functions over this set to be considered, and the restriction is to be polynomial-like functions over this space. Right. So, yeah, so we are interested in this algebra of global functions, which is a commutative C algebra, which is by definition of the quotient stack. The algebra of global functions of this quotient space is equal to the G invariant subspace of the function algebra before quotient, right? And since, well, this is finitely generated, this is a fine algebraic variety. So you know the meaning of this function ring. Then take the G invariant subspace. So this can be just taken as a definition of the algebra of interest. Okay, so this space is very classically important and studied by many aspects of mathematics and physics. And so, for example, from the aspect of two-dimensional gauge theories or three-dimensional Chern-Simons. So from such a physical background, one may sometimes want to quantize the space of the moduli space of G local systems in a certain sense. And mathematically speaking, there are several formulations of quantization, but today I want to focus on its algebraic aspects, namely it's the deformation quantization approach. So it means we want to deform this algebra of global functions into some non-commutative algebras in a nice way. Okay, so for such a problem of deformation quantization of this moduli space, a classical approach is given by so-called skein algebra theory. So I want to just briefly explain the flavor of this theory. So here G is the algebra of G. And the Gauss skein algebra is very roughly speaking defined in this style. So the skein algebra S is defined to be Firstly, the free vector space here, the quotient is the Lorentz polynomial ring of some formal quantum parameter generated by the object so-called gay webs on the three-dimensional manifold sigma times interval, modulo certain gay skein relations. And it's widely expected that for such algebra, such a skein algebra gives deformation quantization of the algebra of interest, the function ring of the moduli space. So what are the objects in consideration? So firstly, what is a gay web? So gay web on the three-dimensional manifold is embedded trivalent graph. Firstly, an embedded trivalent graph, and each edge of the graph is colored by certain fundamental weights, which are corresponding to the fundamental representations of G, and together with the orientations of the edges, such that around every trivalent vertex, the orientation is either a sink like this or source. So this is the orientation rule. And on the compatibility of the colors, so this data is sometimes called colors, is such that the dimension of this invariant subspace of the triple tensor product is one-dimensional. So this is the restriction on the colors. So for example, in the SLN case, we may have a trivalent vertex like this. Yeah, pi a denotes the eighth fundamental weight. And in this case, this compatibility condition is equivalent to saying that the a plus b plus c equals to n in the dimension of SL. So the meaning of this condition is that recall that the eighth fundamental representation is the eighth wedge product, eighth exterior power of the natural representation. So, so for example, if you think that a vector in this representation is carried in this edge, so we have so eighth wedge vector carried in this edge, and bth wedge vector like this along this, and cth wedge vector along this edge. Then we can form their wedge product to get nth wedge vector, nth exterior vector in the n-dimensional vector space. Then if we pair it with the standard volume form, we get value in C. So in this case, this trivalent vertex corresponds to taking the wedge product of three vectors in these representations geometrically. Yeah, so yeah, in this way, you may imagine that given such a gay web on a three-dimensional manifold, you get a function on the moduli space of local systems by forgetting their height information and applying these wedge product local operations, and then finally take the trace. Yeah, anyway, that's the feeding of the gay webs. And the gay skein relations determines how to resolve a crossing in the projection diagram in the 2-dimension. So if we have two such strands, this gives some rule how to resolve this crossing. And I don't write down the formula, but it's type by type determined by according to the R matrix of the quantum group UQK. For example, in the SL2 case, this is the nothing but the well-known Kaufman bracket skein relation, which resolves this kind of crossing to into the horizontal direction with the power q and the vertical direction with the power q inverse. Here it seems no colors because we have only one fundamental representation in the SL2 case, so we can ignore the color. And also this is self-dual, so this is the reason why we don't need the orientation on the edges. But in general, the reversing orientation, we get the dual representation. Okay, that's the just a rough explanation of the skein theory.
I have a question.
Please.
So this skein algebra that you described for type other than A and rank higher than 2, that's also studied by some people?
Yeah, as far as I know, for example, the type C and skein algebras recently studied by several people, I think. I forgot their name.
So is that only a recent result?
Yeah, I think it's relatively recent.
Okay.
Sorry, I'm trying to remember their name.
No, that's fine.
Yeah. Actually, yeah. I think there are several works on type C and case. And I think the type B case is Lagrange dual.
Yeah. So you say that there are references that deal with these other types?
Yeah, at least for type C. But
Okay.
I don't know any reference for the type D and case. And also it's the exceptional cases. Of course, the type G2 case is studied by Kupaba.
Right. Okay.
Yeah.
Thanks.
Yeah, thanks for that question. Okay, any questions? Or any other questions? Okay, so then this is the story for the closed surfaces. But nowadays, one may also want to cut and glue the surfaces to localize the program to the smaller pieces. So in this way, we get we are naturally led to the notion of the multi-surfaces. So for example, if we want to cut a closed surface along a loop, then we may get a surface with boundary, but you can recall the boundary component as marked points by shrinking the boundaries. Then we get something like genus 1 surface together with 2 marked points. This is the punctured surface. And sometimes we may want to further cut the surface into smaller pieces along an either arc that connects the marked points. Then we get this kind of surface with boundary together with 2 marked points only. Maybe this rule can looks odd, but this rule is, I think, very compatible with, for example, irregular Riemann-Hilbert correspondence. So this is, I think, why the marked surfaces naturally appears in this story. So in general, marked surface is a pair of the surface, this kind of pair where sigma is a compact oriented surface with boundary, and M is a fixed finite set. So, and in general, we can consider interior marked points, but today, to consider quantum cluster algebras, I assume that all the marked points on the boundary. So a general figure is like this. Okay, and also a condition with some hyperbolicity condition. So in this picture, the marked points are here and here and here. And we also use this notation B to indicate the set of boundary intervals, which are connected components of the boundary minus the set of marked points. So here is one boundary interval, and here is another boundary interval. And here is also a boundary interval. So we have as many boundary intervals as the marked points in general. And we will sometimes simply write as sigma when the choice of marked points is clear from the context. This is my notation for a marked surface. So in this setting of the marked surface, Fock Goncharov introduced the following extension of the original moduli space of G-local systems and found that this extension gives many interesting properties to this space. So let A G sigma. So here sigma is a marked surface and G is as before, simply connected, same simple group. And then AG sigma is the moduli space of decorated twisted G-local systems on the marked surface. Here, what is the decoration? So the contents of the moduli space is illustrated in this picture. So here, as before, we have a local G-local system over the compact surface. So we have principal G bundle together with flat connections. And the decoration means here, the assignment of a flat section of this associated bundle with the fiber G mod U class. Here we fix the maximal important subgroup U class. So for example, in the SLN case, we may fix this upper triangular unipotent matrices to be U class. So we just fix the standard one inside the group, and then consider this homogeneous space and form the associated bundle with this with fiber G mod U plus. And then we choose a flat, locally defined flat section of this associated bundle near each marked points. And they are denoted by this flag-like symbol in this picture, right? And well, there are a technical thing hidden in this twisted terminology, but today I don't want to mention to the this twisting. But this is just an adjustment of this moduli space by a sign to ensure the positivity structure. So in order to make the transition functions between cluster charts to be positive maps. So we assign we adjust the signs in the level of spaces in some way, but just forget about it in this talk. Okay, so roughly speaking, this parameterizes the G-local system as before, together with flat sections near marked points. Right, then just as before, by taking the monodromy homomorphisms and by collecting the flat sections to a single point via parallel transport, we get this quotient stack description. So we have the monodromy homomorphisms here, and we have elements in this this homogeneous space given by the value at the one point of these flat sections, modulo the gauge equivalence. So this is the description as a quotient stack. So in particular, the function algebra of this moduli space is by definition the G invariant part of this space before quotient, the function ring of this space before quotient. So as a simple example, let sigma be K1, which means a disk with K marked points on its boundary, like this. This is the meaning of K1. Then we have no monodromy homomorphism in this case. And we know also that the function algebra of this homogeneous space is by the Peter-Wiles theorem. It's equal to the direct sum of irreducible representations, like this. Right? Then, in this case, the moduli space consists of the G orbits of M copies of this homogeneous space. So its functioning is the kth tensor products of irreducible representations and take the G invariant part. And this space is very important in representation theory, which is the multiplicity space or the space of intertwiners. So this shows that our moduli space includes such important objects. Right. And one outstanding feature of this moduli space that they found is that it admits a natural so-called cluster K2 structure or the cluster A structure. So this is a particular kind of address on this space. Namely, so roughly speaking, the cluster K2 structure consists of birational isomorphism, birational isomorphisms between this moduli space and algebraic torus, which is a product of C star. So if you are not familiar with the algebraic geometry, you may just think that this is a global coordinate up to some divisors, parameterized by a certain set. And the property is that for any of such two coordinates, their transition function is given by a rational map of combinatorial form for the cluster K2 transformation, which is this is a rational map of special kind, which can be computed combinatorially. So this gives a special, a very special kind of address on a space. And they found that this space has such special coordinate systems. And as a historical remark, for type AN, SLN case, such a structure can be has found by Fock Goncharov in the paper. And for type BCD, classical types by E&D. And for the general case by Goncharov Shen in their relatively recent paper. Right. So it was, I think it was very hard to explicitly found such structure. So this is very special at last. So in particular, such a special structure defines a special subalgebra, so-called the cluster algebra, inside the field of rational functions of this moduli space, in the sense of forming Zelevinsky. And then following the framework of Berenstein, Zelevinsky, we can also consider its quantization for the quantum cluster algebra, which recovers the original cluster algebra in the Q equals to 1 limit. So I think it was one of the main motivations to introduce cluster structure. namely to find the natural quantization of the functions over the moduli space in the context of higher quantum time theory. And yeah, anyway, the cluster structure and the framework of the cluster algebra allows one to somehow define the quantization of this important moduli space. So roughly speaking, this already gives a quantum theory of the moduli space, but well, actually the precise statement is needed to claim that it indeed deforms the algebra of global functions. So here's our first main theorem, which is by myself and together with Hironori Oya and Linhui Shen in our paper in 2022. So we assume some mild conditions. So as before, let's the marked points be all on the boundary. And we assume topologically that we have at least 2 marked points. And the representation theoretically, we assume that G is not of type exceptional types E8, F4, nor G2. They are excluded. Then under these conditions, we get that the cluster algebra is indeed isomorphic to the algebra of global functions on some open subspace of our moduli space. So this times notation stands for the kind of generic part of this moduli space. And well, taking a generic part corresponds to localizing the function algebra in a certain way. But under such small localization, we get this equality as C algebras. So, and I want to explain the ideas of this statement in my talk. So here's my plan. So in the remaining time, I want to explain more on the classical geometry, focusing on the ideas of the proof of this theorem. And if we have enough time, I want to also mention its quantum aspects, its relation to skein algebras. So any questions so far?
In the statement of the theorem, you have 2 curly A's in both sides.
Ah, yes, that's the
left one is the algebra and right one is the space.
Yeah, sorry, that's my apology in my writing. So yeah, there are 2 curly A's. So here, weakly curly A is Moscow A in my notation, and highly curly A stands for Maastricht A.
So in the paper, they look different.
Yeah, in the paper, you can clearly English, but it's due to my writing. So please let me know if, when it's ambiguous.
And for the cases that are not dealt with in this theorem, for example, when there's only 1 marked point, or when the G is one of the 3 exceptions that you wrote. So it's not that the theorem is false, but the arguments doesn't work.
So yeah, at least this assumption, I think it's just a technical assumption. So okay. I think this assumption can be dropped in the future. Yeah, so this is just a technical matter, I think. But for this exceptional condition on the gauge group, I don't know. So,
you mean the statement might be false for these 3 cases?
Yeah, might be false, but might be true.
Okay.
So for type G2 case, So at least for the type G2 case, when the surface is small enough, for example, for a triangle case and a square case, in that case, yeah, this statement is true. So, so the key problem is to prove the A equal U equality. The class algebra coincides with the upper class algebra.
Yes.
So, yeah, in our approach, in this, okay, so roughly speaking, the strategy is as follows. So we first have this inclusion by the upper bound theorem. So the cluster algebra is always the subalgebra of the upper cluster algebra.
Yes.
And we first show that this upper cluster algebra coincides with this function ring algebra of this moduli space.
Yes.
So this is by an algebra geometry, algebraic geometry argument. By comparing the cluster variety with the moduli space up to codimension 2. And then we use these assumptions. So this equality is holds without any assumption.
Okay.
And then we use this assumption to conclude this equality.
Okay.
So this is needed to specify a generating set of this algebra to be a special one. Yeah, so but as another strategy, we may directly show this equality by some combinatorial manner, independent of the geometry.
Yeah.
For example, by the Banff algorithm of Euler, we get the equality of these three algebras. So in the G2 case, for triangles and squares, I somehow prove the Banff property for the cluster algebra to get a equal U result. Then it's fine. But for general surfaces, I don't know.
Okay.
There are gap between these algebras. Yeah.
Okay. Thanks.
Any other questions? I'm happy to answer more easy questions. Yeah. Okay, then let's proceed to section 2. So let's recall our object. So our moduli space A is this quotient stack, the moduli space of decorated G-local systems. So first of all, I want to explain the geometry of the meaning of this space, G multiplus, and why I use the flag-like notation in the picture. So this is, so let's, for example, G be SLN. Then this homogeneous space is isomorphic to the moduli space of the following objects. Here, large V, V bar denotes flag in the n-dimensional space, which is a sequence of subspaces of Cn, such that the ith subspace have dimension I. So this is a nested sequence of subspaces. And small v denotes its decoration, which is a non-trivial element of the determinant line of each subspace. So this is one-dimensional subspace. So we pick one non-zero vector in this line. And as the SLN condition, we assume Vn to be the standard volume form on Cn. And this data is usually called a flag because it looks like this picture. So we firstly have the zero-dimensional space here and one-dimensional space through it. And the second data is the two-dimensional space that contains this line. Then it looks like a flag. And then we get we also choose higher rank, higher dimensional subspaces. And this is the reason why this is usually called a flag. And also, this data of decoration, roughly speaking, specifies the framing of these subspaces. Okay, so this is the contents of this homogeneous space. And together with this understanding, so I want to explain the two kinds of functions naturally defined on this modular space. One is the cluster coordinates, the other are the reason lines. So let us first explain the cluster coordinates on this modular space following Fock Goncharov. So the general theory is very long, so I want to specify to the SL entries. So let us choose an ideal triangulation of the surface. The coordinates are associated to such a choice of triangulation, which is a triangulation of the surface only consisting of simple arcs connecting marked points. So we make a triangulation of the surface only using these arcs connecting marked points, something like this. And in this picture, we may need more and more arcs to triangulate the surface. But under the, hyperbolistic condition, we can check that such an ideal triangulation always exists under this condition. Right. So pick up such a triangulation, and let's focus on one of its triangles. Then the local picture is like this. So this is our triangle, whose vertices are necessarily marked points on the boundary. So locally looks like this. And let us consider a point on the modular space. So we get a G-local system together with the decoration. So in particular, at these 3 points, we have the 3 flags associated, which is denoted by F, G, H. And you know, originally they are just locally defined flat sections, so lives in different spaces. But you may fix one point in the interior of the triangle and parallel transport them to this common point, right? Then inside this common fiber, which is Cn, so we consider the associated Cn bundle, for example. Then inside this common Cn, these 3 flags defines 3 sequences of subspaces, Fa and Gb and Hc in a common Cn. And to define the coordinates, let's take 3 non-negative integers that sums up to n. Then we define the cluster A coordinates, A of ABC on the triangle T to be this function. Yeah, here I should explain the notation. Here I wrote each decorated flag F by tuple F dot and small f dot. And FA stands for the F decoration, living in debt of FA. And similarly for the other 2. So for example, FA is on F's exterior vector, and GB is a B's exterior vector, and HC is a C's exterior vector. Then taking their wedge product, we get an L's exterior vector, which can be paired with the standard volume form of the SLN local system. And then, so this pairing at this fiber gives you a complex value, which defines a function on the moduli space. Okay, so this is the definition of the function. And then we collect these functions over all triangles and over all the triples of integers to get a collection of global functions on this moduli space. And this is in the cluster algebra language called a cluster on this moduli space.
I have a question.
Mm-hmm.
So in the definition of the function, if I change the role of FGH cyclically, then the function might change by a sign a priori.
Yes. A priori, yes.
Yeah.
So that's the point I hid the in the definition of the moduli space. So to remedy that point, exactly that point, we need to twist the moduli space by signs. So
right, and this is only necessary when n is even.
N is even, right? Yeah. N is even.
Okay, thanks.
Yeah. So after, so precisely speaking, we should be also careful about the paths that collectively refract to common points. So as you know, if we consider twisted local systems, it's actually defined on the punctual tangent bond of the surface. So we need to care about the framing of the paths. So so anyway, that's the technical point, but with the care on the framing of the power transport passes, we may collect the three flags to the common point and take this function. And then somehow right. Yeah, so that's the actual situation to remain the sign problem. Yeah, but anyway, after such twisting, this function is well defined and cyclically invariant. Yeah, in this case. Okay, then this is one cluster associated with a triangulation. And well, actually, these functions can be assigned to the vertices of the following quiver. So here is the picture for the SF4 case. So to each triangle, we draw somehow subdivision of this triangle, and then assign appropriate orientations to get the quiver. And the vertices of the quiver can be coordinatized like here 310, and here 220, and here 130, and here 301, and so on. And we think of these functions sitting at the corresponding vertex. And so ABC sits on the vertex labeled by ABC. And then under this assignment, we have compatibility condition of this kind. So for example, if we consider A301 here, then it's independent of the triangles that comes from. So, I mean, for example, in this case, B is 0. So it means that we ignore the G here, B equals 0. So by convention. So this means that it only depends on the two flags F and H and independent of G. And this dependence is compatible with its location, right? So this is on the edge, f on h. And then, well, viewing from this right triangle, this sits in the position 310. So this is 310 seeing from the right triangle. But well, this gives the same function viewing from the right triangle. Then in view of this observation, the true parameterizing set of this collection of functions is the vertex set of the quiver. So we actually have as many functions as the vertices of this quiver. So it's nice to consider this pair of functions together with the quiver, which is called a seed in the cluster community. And then the theorem of Fock and Goncharov is the following. So firstly, this collection of functions gives a birational isomorphism. So it's a global chart up to devices. And secondly, so it depends on the triangulation. So if we change the algebra triangulation and consider two such triangulations, then we have two kinds of global charts here. And the statement is that their transition function is given exactly by the cluster K2 transformation. So this has a very specific form controlled by the quiver. Right. And this is a rough explanation of the cluster theory, really rough explanation. So given us, so we have operation among the seeds for the seed mutations, and we have as many mutations as the number of vertices. So for each choice of the vertex of the quiver, we have the corresponding seed mutation in that direction, which creates a new seed from a given one. So given AQ, this creates another seed, A prime, Q prime, in a certain combinatorial explicit rule. And in particular, the transformation of these variables are called the cluster K2 transformation. But I don't write down the formula. So schematically, starting from the, for example, seed associated to an algebra triangulation, we may perform as many mutations as the number of vertices in different directions to get many other seeds. And then we can also apply the seed mutation to the obtained one iteratively. So we have mutations, and so on to get a large collection of seeds. And sometimes the statement of the second statement of Fock-Goncharov says that in this network of mutations, one may find the seed associated to another triangulation. So in some sense, this graph of mutations is connected. Right. So applying the cluster transformations, seed mutations many times, we get a large collection of, for example, in particular, large collection of functions. And this set of functions is called the cluster. These so obtained functions are called the cluster variables. Right. So the cluster algebra is defined to be the algebra, subalgebra generated by all of these cluster variables over C, plus inverses of frozen variables. So maybe I skipped the explanation of frozens, but here is the quiver drawn on the surface. And if this is a boundary, the vertices on the boundaries declared to be frozen. And this means that we don't mutate at such frozen vertices. So this should be written like I unfrozen. So the mutations are restricted to the unfrozen directions. So interior vertices are allowed to be mutated, but the boundary vertices doesn't mutate. Yeah, anyway, as a small matter of convention, we include the inverses of frozen variables here to the definition of the cluster algebra. And this a priori sits in the field of rational functions because the cluster K2 transformation is a rational transformations. And we don't know all of the functions that created by mutations iteratively. So of course, initial functions associated to triangulations are known to be global functions, but so obtained functions may have poles in the denominator a priori. So the natural position that the cluster algebra sits in is the field of rational functions. But our theorem states that, as I mentioned in the introduction, this kind of equality, so that actually all of these cluster variables are globally defined functions over this moduli space. So this is one point. So here, this is a point I explained the open subspace view roughly. But so this A times denotes the open subspace obtained by imposing the genericity on the consecutive flags on the boundary. So, well, the definition is written smallly in this here, but this imposes an open condition on the pair of on the position of a pair of flags. Yeah, but anyway, this defines certain open subspace. So yeah, taking an open subspace amounts to localizing the function algebra. So this involves the small localization of the function algebra, and actually this corresponds to including the inverses of frozen variables. Right. So this is also another technical point that, yeah, we actually need the inverses of frozen variables and this localization to obtain such equality. So without inverting the frozen variables, we don't know such equality. Okay, then as I shortly mentioned in the introduction, here's the line of the proof. So firstly, in general, we know that the cluster algebra is contained in the so-called upper cluster algebra, which is the function ring of the so-called associated cluster K2 variety obtained by gluing the cluster charts via the cluster K2 transformations. And then we compare this cluster K2 variety with our moduli space. And we see that these two spaces are equal when we ignore the difference in codimension greater than 2. Then a standard fact of algebraic geometry says that two spaces equals up to codimension 2 implies that their function rings coincide. Then we get this equality. So again, this needs no restrictions on the surface and the gauge group. And for the other direction of inclusion, we investigate this function algebra, and we show that this is generated by matrix coefficients of Wilson lines, which is the object I'm going to explain in the next slide. So this is a general result, but under these conditions, so we can show that this algebra is can be generated by more specific set of matrix coefficients of specific Wilson lines. And by computing such special Wilson lines in terms of coordinates, we can show that they are all the cluster variables. Then it establishes this inclusion. And this is the line of the proof. So in particular, this Wilson lines are one of the important objects. So I'm going to explain this object. Right. So we have 30 minutes left. Okay, so here's an explanation on the Wilson lines. So first, preliminary observation. So it's actually not so new object. So it's very classically used in literature. So observation is that suppose we are given a path C in the surface running from one boundary interval to another boundary interval. So connecting two boundary intervals, which may not be simple. So like this. And suppose we have a G-local systems on the surface. So we have, for example, fiber over this initial point and a terminal point. And then further assume that we are given two local trivializations of these local systems at the initial and terminal marked points, which means that we have fixed we have a point on each of these fibers, so S1 and S2. And then, as in the definition of the monodromy, we can parallel transport the first point along this path towards the final fiber. But in general, this differs from this secondary chosen point, right? Then, as in the case of monodromy, we can measure this difference of these 2 points by a unique element of G. And this is the denoted by GC L of S1 and S2, which is arc version of the monodromy, right? But the point is that, of course, this element highly depends on the choice of the local trivializations. So in order to define such functions, we usually need to extend the moduli space, including these choices of local trivializations, but we don't want to do this. So we want to use the decorated G-local systems without any additional choice of local trivializations. But a nice observation made by Goncharov Shen is that generic decoration in a certain way gives local trivializations on the boundary intervals by using the notion of so-called pinnings. Yeah. So anyway, roughly speaking, yeah, this pair of generic flags determines in some way local trivialization over this interval. So this is nice. So we apply this construction to our moduli space. So given decorated G-local systems with generic condition, we can automatically define the local trivializations denoted by PE1 and PE2 over the initial and terminal points of the given path. Then we define GC to be this arc monodromy corresponding to these local trivializations. Yeah. And here in the second entry, we need a small correction by linking involution. But anyway, we get such functions. And this defines a morphism of stacks, and we call this one as Wilson lines. as line version of the monotony, which is also called Wilson loops, mainly in the physics literature. So, so we have G-valued functions on the moduli space. And if we take the matrix coefficients here, then we get a C-valued function, right? So we can consider any representation of G and the vector and covector in that representation to form a C-valued function. And then, well, a natural proposition is that this function algebra can be generated by matrix coefficients of Wilson lines. So the information of all Wilson lines determine the decorated G-local system. And here is a very important transition formula. So if we consider, for example, the generalized minors of Zelevinsky, Berenstein Zelevinsky, maybe. This is a very special kind of matrix solutions. And then this can be explicitly computed in terms of the cluster variables. So this is given by some explicit cluster variables on a square divided by certain frozen variables. So yeah, what y square appears is that, so here we consider special kind of Wilson lines called the simple Wilson lines. So we assume that the Wilson line sits in image of an embedding of a square neighborhood, a bound neighborhood. So in particular, this line is supposed to be simple, having no self-intersections. And the initial and terminal boundary intervals are distinct. This is the condition. And then we can compute the matrix coefficients of Wilson lines along this line in terms of these 4 decorations, which means that the computation localizes to the square, right? So in this special situation, we can explicitly compute the generalized minors by cluster variables on the square. Okay. So for example, in the SL2 case, in this case, we know that we know all the cluster variables. So in this case, the cluster variables are corresponding to simple arcs. So we can represent the cluster variables by arcs. So in this expression, the Wilson line, this Wilson line on the square have this matrix representation. So for example, 2-2 entry corresponds to the cluster variable here. And 1-1 entry corresponds to the cluster variable divided by 2 frozen variables here. And the key point, final key point is that, and so finally we use these conditions. So under these conditions, this function algebra can be generated only by generalized minors of simple Wilson lines. So this condition ensures this part, and this condition ensures this part. So if we have only one marked point, for example, we need to consider non-simple Wilson lines whose computation becomes harder. So because it doesn't localize this to a computation in the square, so we need to elaborate more. And this condition ensured that the algebra functions over G is generated by generalized minors. This is the representation theory condition. But without this assumption, we need more functions to generate the matrix coefficients. So, well, this formula doesn't apply, right? Yeah. So the problem is that, yeah, for example, in the type G2 case, we have a 7-dimensional representation, and well, we have y1 and minus y1 and something like this. And the point is that we have a weight 0 state in the middle, and the matrix. So we have the matrix coefficients corresponding to this state. So we have the matrix coefficient delta 0, 0, for example. And actually, we need this function to generate the function in OG. Right. But this is not a generalized minor, so we don't know how to express this function in terms of the cluster variables. So this is the problem in general. Yeah. But yeah, under this condition, so we can compute the generalized minors of simple Wilson lines in this form. And as this formula tells, this is written in cluster variables modulo frozen variables, which is in particular an element of the cluster algebra. Then we get this equality. And this completes the proof of the main result. Yeah. And summarizing, we get an isomorphism between these two algebras, which in particular gives us two generating sets. One is the cluster variables in this side, and one is the matrix coefficients of Wilson lines in this side. And we have an explicit transition formula between them. Yeah, so any questions so far?
I have a question.
Please.
So on the left screen, the first line of the proposition. So that needs some algebraic geometry.
Yeah, but it's very simple. So so yeah, this can be made more explicit statement. So we have many Wilson line functions. So so gathering all the Wilson line functions, we get an embedding of this one. Embedding. Something like this. Here, this is somehow something called a groupoid character variety. And here, this is the fundamental groupoid of the punctual tangent bundle with objects corresponding to boundary intervals. And by studying the definition of the Wilson line, you may find that the concatenation of lines corresponding to the product of Wilson lines. Right. Then it means that the collection of Wilson lines gives a morphism from this fundamental groupoid, where the composition is given by the concatenation of arcs to the groupoid G, where the composition is given by the product operation in the group. So this is a well-defined map. And then you can check that this is indeed an embedding, closed embedding. By just seeing how the decorations as G local systems can be recovered from Wilson lines. For example, the monodromy can be recovered from the Wilson lines of this form. Right? The monodromy is a particular case of Wilson line in this formulation. And also the relative position of decorations can be also measured by Wilson lines because it refers it refers to the decorations here. So by seeing this component in the Wilson lines, we can recover the relative positions of decorated flags up to gauge equivalence. And then we can recover the decorated G local systems, meaning that this is an injective. And yeah, from further computations on the relations among the Wilson lines, we can directly compute the defining relation of this moduli space to conclude that this is a closed entity. And then it means that this, this algebra is like this. So on this space, modulo by ideal corresponding to this closed condition, right? The closed condition corresponding to the quotient of some ideal. And then, rephrasing this, so this is trivially generated by matrix versions of Wilson lines by its definition. Well, actually, this is shown to be finitely generated, so that this is indeed an algebraic variety. And the function name is by definition generated by matrix versions of Wilson lines modulo some relation. Right. So in particular, we get this statement. And of course, the relations among Wilson lines can be explicitly write down. So we have an actual representation of this algebra.
Okay, thanks.
Yeah. Another question? Okay, then let's proceed to the quantum aspects in the remaining time. So here's a quick introduction to quantum cluster algebra due to Berenstein, Zelevinsky, plus Goncharov, Shen. So the basic idea is to deform each coordinate system like this, right? So at the classical level, of course, the cluster variables are commutative, but let's deform them to a quantum torus by choosing a skew-symmetric matrix pi. Just choose. And then, of course, if we randomly choose such a skew-symmetric matrix in each cluster coordinate, of course, it's not compatible with the coordinate transformations. But it's known that if it is compatible with the quiver in some linear algebraic sense, then these non-commutative deformations are coherent in the sense that they can be connected by a quantum version of cluster transformations. Yeah. So the idea is the coordinate-wise quantization, and then glue them into a global object. And then we get a quantum cluster algebra denoted by AQ. Well, this is a general theory, course, so it can be applied to a general cluster algebra associated to a mutation class of quiver. And anyway, this gives a quantization of the cluster algebra. And here is a slight reformulation given by Goncharov, Shen, which is important to our formulation. So here is well, this choice of compatibility matrices due to Berenstein, Zelevinsky, but Goncharov, Shen found that this choice corresponds to the following geometry. And here's a bit on the geometry of the cluster variety. So originally, we have two kinds of cluster varieties called cluster K2 variety and cluster Poisson variety. Here, X unfrozen stands for the cluster Poisson variety without frozen variables. And we have naturally so-called ensemble map between these two kinds of cluster variables given by the quiver exchange matrix, but on the restriction on the frozen variables. And in order to lift the ensemble relation to the entire X cluster Poisson variety, we need to pick up one lift of this ensemble map by choosing some entry on the frozen direction. And this is called an extended ensemble map. And then Goncharov Shen noticed that this choice of extension of the ensemble map exactly corresponds to the choice of compatibility matrices. So in other words, the choice of the extended ensemble map determines a quantization direction. And I forgot to mention that, of course, this quantization is not unique, depending on the choice of the matrices. But this choice that exactly corresponds to the choice of extended ensemble map. And actually, they provides geometrically, from the moduli point of view, the canonical way of extension, a natural way of extension from the geometry. So we choose this choice of extension coming from their geometry to get the quantum cluster algebra. So in what follows, we consider this quantization of the cluster algebra. Then regarding this quantum cluster algebra, here is our general expectation, which is just a conjecture in this most general setting. So our expectation is that there should be certain well-defined two kinds of skein algebras, which we call stated skein algebra and denoted by S of B, which stands for the boundary condition. And another type of skein algebra called the clasped skein algebra, S of M, defined for any D algebra and any marked surface, such that this quantum cluster algebra is isomorphic to firstly reduced some quotient by an ideal of this stated skein algebra, and also it's expected to be isomorphic to some boundary localization of this classed skein algebra. So this is our expectation. And if they are true, these two kinds of skein algebras should be isomorphic. And the relation between these two skein algebras is called, well, we call this state clasp correspondence. So let me explain more on its contents. So roughly speaking, the stated skein algebra should be defined like this. So as I explained in the beginning of the talk, the classical skein algebra is somehow defined. So in the closed surface case, consisting of gay waves together with gay skein relations in the interior. So we only need to specify the boundary behavior at the boundary. So the stated skein algebra considers the skeins with gay waves having the endpoints on the boundary intervals, which corresponds to this notation, together with height informations. And also a specific thing is that we should assign states at each endpoint of the web, which corresponds to the labelings of the basis vectors of the corresponding representations that they carry. Plus, so we should consider modulo such gay waves modulo suitable stated skein relations. So this is what we should define in general in the future. And the classical meaning of the elements is the following. So classically, as I talked, we can consider the matrix entries of the Wilson lines. So Ji entry in the representation will be lambda. Then this should be lifted to element of this stated skein algebra given by this oriented arc together with the color lambda, representation lambda, with the state ij on its endpoints. So in this sense, I want to think of this stated skein algebra as a quantization of Wilson lines. But of course, in general, we should have we have trivalent graphs as an element. But as at least as a generating set, I expect that they are generated by quantum Wilson lines. And then the classed side is similarly defined, where the boundary conditions that is that the endpoints should be on the marked points rather than the boundary interval, as in the picture. And well, of course, we also need suitable definition of skein derivations regarding the behavior at the marked points. And the classical meaning is that this corresponds to cluster variables. So for example, the cluster variables that I explained in the SLN case should be corresponding to this given, having endpoints and marked points, right? I hope this is convincing because of the two explanations of the meaning of the GWeb and the definition of the cluster variable. That's the same. And then, so to what extent this conjecture is established? So I will illustrate the state class correspondence for the SL2 case, which is also treated in the paper of Tanley and Aoyu in less explicit way. But in this case, the correspondence is as follows. We construct a map from the stated side to the classed side by identifying the end with the state 1 with this left turning arc together with the inverse of the frozen variable. And the state 2 arc should be identified with the right turning arc. Then, so for example, this algebra without localization responds to, so is generated by this kind of elements, so that this part corresponds to state 2 part, totally state 2 part of this algebra. And Liu gives, Liu considered this kind of embedding in this form, and abstractly argued that this embedding induces isomorphism after localization. But our point is to write down the inverse map in this form, which is indicated by the classical geometry. And you should compare it with the previous formula for the Wilson lines. So, for example, 2-2 entry of the Wilson line is written like this. And then locally, so by locally viewing each end intervals, we get this correspondence, right? So as I mentioned, the 2-2 of G should correspond to stated arc with 2-2 states. And then this formula tells us that this should be corresponds to this other arc. So this is the idea, right? So based on the transition formula, as I explained in the classical setting. We also have explicit isomorphism for the rank 2 Lie algebras. So this conjecture is established for SL3 and SP4 already. And we are also trying for the G2 case. And general statement so far is that for get rank 2, or sorry, SL2, SL3, and SP4, then we have established this isomorphism together with inclusions of these algebras. And also these inclusions, of course, I expect these inclusions should be isomorphisms. And at least in the classical level, they are isomorphisms. Yeah. So this is the current status. But as I mentioned, the transition formula of Wilson lines and cluster variables tells us the general correspondence. So I expect this conjecture should be true in general based on that formula. So okay, so that's the end of my talk. Thank you for listening.
Thank you. Let me first end the recording.